from the University campus Biomedical in Rome, Italy. He is currently Assistant Professor in the Biomedical Engineering Department at the University of Delaware. Please join me this morning in welcoming Dr. Sergi.
Good morning, everyone, and thanks to the organizing committee for the invitation. I will provide an overview of an emerging field that of using robots to support the process of neurorehabilitation, and by doing that I will provide an overview of what we are doing in my lab, the Human Robotics Lab, that has been recently established here at the University of Delaware. Okay, so as an engineer, I will give just a little bit of context that will be useful for us to understand some basic principles, but I will not go into the details of something that as clinicians and medical practitioners you will know much more than I do. So, neurorehabilitation is a broad term, is a medical process aimed at promoting functional recovery after a neurological injury, such as stroke. It's a growing challenge of modern society. The mechanism of disruption is very well known. A vessel obstruction, the resultant reduced blood flow, lead to neuronal death, and disruption is caused both in the region that receives reduced blood flow for some time, but also in surrounding and distant and functionally connected areas, such based on the process of diastasis. So the consequences are substantial. 50% of survivors are left with hemiparesis after 6 months of injury. 30% require walking assistance. And this happens although there are some endogenous pathways that are capable of promoting recovery. A catch-all term here is the process of neural plasticity. A concept here that's shown in this figure is that of vicariation of function. This is the normal representation for hand knob turning task. What happens after stroke that partially disrupt areas that are included in the nominal functional representation is that other areas can be recruited to promote motor function. However, which areas should take over loss function and how to promote recruitment of additional areas to induce functional recovery is still unknown. So there are, however, some observations that have happened at a strikingly recent time frame, you could say. So this is a seminal work by Nudo et al. In Science, 96. So it's relatively recent. And what they have observed is that neuroplasticity is behavior dependent. So they have done cortical recordings of monkeys and mapping the functional representation of motor cortex. And so the different colors here refer to different body segments that are stimulated with electrical, that move based on electrical stimulation. And so you see that there is an invert in this area that affects the wrist forearm representation. And after repetitive movement exercise, what happens is that these brown areas show up somewhere else. So given the repetitive movement exercise, the functional representation can be remapped based on recording. And this is not something that was systematically observed 100 or 150 years ago. This is like relatively new knowledge. And so based on that, a key concept that's used in neurorehabilitation is to use movement therapy to promote an activity-dependent plasticity that then improves motor function. And so as engineers, we like to make simplified models that can allow us to understand very complex processes like stroke recovery. So here we have a block that's treatment. Treatment influences neural plasticity. And then ultimately that leads to functional recovery, right? So if we want to get here, we need to apply treatment to this intermediate block, right? So, and this was known in the conventional wisdom of rehabilitation since several decades. So Bobath is one of the development of a applying motor learning principles to stroke rehabilitation. And so what he says is the greatest art of treatment is to know where and for how long to take the hands away, the hands of the therapist, so that the patient has a chance of his own control whenever possible. And so this was then, again, formulated in a quantitative way, in this case in treadmill training on rats affected where they had a surgically induced spinal cord injury. And so they show that neuroplasticity is triggered when the training program allows for active participation of the subject. And they formulate what's called the assistance needed approach. So this was happening while technological development enabled what I've called here, a little bit emphatically, but the human robotics revolution. So from a technological side, we can see that there was an era where robots were confined in cages and were dangerous things that have to move as fast as possible, and as a consequence the human operator could never get in the robotics area. To an era where robots can be developed and used successfully for physical interaction with humans. And one of the fields that has benefited from this, that I call revolution, is neurorehabilitation. So we see here an example of an upper arm exoskeleton, or of a lower extremity system, and of prosthetic devices. Those are also human-applied robots. Okay, so I will focus now on these first two cases, which I call robotics for neurorehabilitation. And so in this field, robots enabled, of course, addressing here the yellow block here, treatment. And what they afford is automation of therapy. They afford accurate and quantitative measurement of recovery, and applying systematic and repeatable assistance. And so we support here transition from art to treatment. And so let's just make the case that how to properly use robots for rehabilitation is a different topic. So I will now describe how they can be used, and the point of how they have to be integrated in shared protocols, and what the optimal role of a human therapist should be. It's a point for later discussion. So I'm going to show some examples here. This is a robot for upper extremity training. It's an already commercial product. And so what it's based on is on developing force-controlled video games that promote repetitive movement therapy. So in this case, the subject is simply asked to go from point A to point B, when in point B to grasp a virtual object by squeezing this little hand module. And in this case, the robot can apply a variable amount of assistance. It can completely do the movement on its own until it can measure that the patient is recovering some part of motor function, and then progressively leave the motor task to the patient. So what they can implement here is a shared assistance protocol. Another case of where robots might be useful for rehabilitation is for gait. And so here on the left you can see an example of using body weight supported therapy training applied by human therapists, and you can see that there are at least 3 therapists being involved in this process, and it's labor intensive, and it's complicated also to keep treatment systematic. Like, how do you know whether the therapist is getting tired? How do you know how much dose of training we are providing? So this can be automated again with robots, and they can be coupled with virtual reality simulations so that you see that you're walking in a more or less realistic environment. And the robot here can provide, again, variable levels of assistance that can be recorded and then analyzed to do effect of treatment dose to recovery. So these are examples of systems that have become now commercially available. Some of the systems developed have underwent large-scale clinical testing, and it's always important, especially for us engineers, to do some type of reality check. So upper arm rehabilitation, this is a large multi-center clinical study where they have compared robot-assisted therapy with a control group. In that case was intensity-matched comparison therapy. So in one case, the patient was doing the upper extremity movement that we have seen in the first video, and in the other case, it was a human therapist who was promoting the same number of movement exercise per session. It happened that the therapy with the robot took about 50% of the time that the therapy with the therapist took. Of course, the therapist does get tired, the robots don't. However, the outcome is actually interesting here. So the gain in the primary outcome measure, Fogel-Meyer score, was positive and statistically significant so for both groups. However, there was no statistically significant difference between the group that received robotic intervention and manual intervention. And it makes sense. At the end, it's not that just the fact that you're interacting with the robot, how much cool that might look, is actually triggering different recovery pathways. So the robots here are tools to automate therapy. And it's a good thing that in this case, they are promoting some type of functional recovery. This type of therapy has been studied under economic and cost efficiency principles, and in the long term, robotic technologies have shown to be to have an advantage. However, a different story occurs for robotic gait training, which is what we see in the right part of this slide. Robotic gait training is very complicated, requires much higher torques and power, and it's more difficult to develop systems that do that properly. And in fact, the first validation studies have shown that there is no significant effect in primary outcome measure. That in that case was a self-selected speed. Can I walk faster after undergoing robotic training? So there are definitely several challenges. So one is from the machine design standpoint. We need to develop machines that can apply high forces, but also need to get out of the way to promote volitional control of movements by subject. Another aspect is on the standpoint of control. How do we deliver this assist as needed type of rehabilitation? How do we understand where and when to get out of the way? And so there are some conceptual frameworks here that I try to show in this slide. So there are two charts here. Let's focus on the left one. So the framework here is called the challenge point framework. And it's a really simple approach to describe motor learning based on a theory developed at the University of Nevada by Mark Guadagnoli. So essentially it's just acknowledging that learning depends on practice, right? And practice is modulated by two experimental factors, skill level, right? And task difficulty. And so they are shown in this figure, nominal task difficulty, and on the y-axis here we have predicted success. So based on the skill level, and this distinguishes between beginners, intermediate user, and experts, we can have these curves have different relationships, right? They have, of course, the predicted success is very high for our low task difficulty beginners, and then drops quickly with task difficulty. Another important factor of motor learning in this theory is represented by viewing motor learning as a problem-solving process. And as a problem-solving process, the amount of information that you can receive as feedback on how you have done is crucially important. And so that's shown in this plot here. So as a function of nominal task difficulty, the amount of information that you gain by practicing on that task at that given level of difficulty has also a relationship that depends on the user. So the user will learn more if it practices at this low challenge region, because it's unknown whether he will be able to accomplish the task or not, right? And then this amount of information is higher for user as the challenge level increases. So essentially, as a function of the individual, we see that what are called the optimal challenge points are for tasks that have a progressively higher level of complexity. This is not surprising. If we want to continuously challenge individuals, we need to expose them to tasks that have a progressively wider level of complexity. And what about a patient, right? So a patient, a neurologically impaired patient, might actually live in this region where the nominal task difficulty is such that predicted success is very low for a wide range of tasks. How do we train these tasks? Where? The role of robots could be that of making these patients beginners, right? Applying assistance so that to enable the region where there is task uncertainty and where there is benefit to practicing. And so to bring the subjects here that have an undefined optimal challenge point into this point where they can start practicing and gain information from success or failure in motor tasks. So this is very much like using training wheels or not using training wheels when learning to bike.